In the previous video, we wired the inputs and outputs of our S7-1200 PLC. But how do we identify that push button in the PLC program? Before we start programming the PLC, there's one important thing you need to understand: I/O addressing. This is the foundation you'll need for everything we'll build in the programming lessons. By the end of this video, you'll be able to look at an S7-1200 I/O address and understand exactly what it means and how to use it in your PLC program. Let's get started. When we program an S7-1200 PLC, we use specific addresses to access its inputs and outputs. For inputs, we use the letter I, and for outputs, Q. For example, an input can have the address I0.0. The next input can have the address I0.1. The same principle applies to outputs. For example, an output can have the address Q0.0. But what do the 0 and .0 actually mean? To understand that, there's one basic concept you need to know: the binary system. Don't worry, it's actually very simple. A digital signal has only two possible states: 0 or 1. These two states are represented by a single bit. You can think of a bit like a simple on-off switch. For example, when a push button is not pressed, its input bit can be 0. When you press the button, its input bit changes to 1. Now, 8 bits are grouped together to form 1 byte. Each bit can independently be either 0 or 1, depending on its current state. So, 1 byte contains 8 bits, numbered from 0 to 7. For example, bit 0, bit 1, bit 2, up to bit 7. Now let's see how we can identify each individual bit within a byte. The addressing is actually very simple. First, we specify the byte address. Then, after the dot, we specify the bit address within that byte. For example, let's look at byte 0. A byte contains 8 bits, numbered from 0 to 7. If we want to access bit 0 of byte 0, the byte and bit part of the address is 0.0. The first 0 is the byte address, byte 0. The second 0, after the dot, is the bit address, bit 0. Now, what if we want to access the last bit of byte 0? The last bit is bit 7, so the byte and bit part of the address is 0.7. The first 0 still represents byte 0, while 7 represents bit 7. Now let's take a bigger example. Suppose we are working with byte 124. Just like byte 0, byte 124 also contains 8 bits, numbered from 0 to 7. For example, the first bit is 124.0. The fourth bit is 124.3. And the last bit is 124.7. The rule is always the same. The number before the dot is the byte address, and the number after the dot is the bit address. So whether we're working with byte 0, byte 1, or byte 124, the addressing principle stays exactly the same. And this is important because the S7-1200 uses a byte and bit structure when addressing its digital inputs and outputs. Now, let's connect this concept to our real S7-1200 PLC. In our current hardware configuration, these 8 digital inputs are assigned to input byte 0. For input addressing, we use the letter I. Then, we write the byte address followed by a dot, and finally the bit address. Remember, 1 byte contains 8 bits. So, each digital input represents 1 bit. The first input is bit 0. The second is bit 1. And so on, up to bit 7. That means these 8 bits make up 1 byte. If the inputs start at byte 0, their addresses are I0.0, I0.1, I0.3, and so on, up to I0.7. So, the idea is very simple. 8 bits make 1 byte, and each digital input uses 1 bit. That's how byte-and-bit addressing works in the PLC. I should also mention that the byte address can be changed in TA Portal, the engineering software we use to program the S7-1200 PLC. In the hardware configuration, we can configure the start addresses of the inputs and outputs. We'll see exactly how to do this in the next video. Now, let's practice with a bigger example. Imagine that we have 16 digital inputs, and in the hardware configuration, we set the input start address to byte 124. Now, the first 8 digital inputs occupy byte 124. Following the same rule, the first input has the address I124.0. The second input is I124.1. The third, I124.2. And this continues up to I124.7. That's our first 8 inputs. Now, we've used all 8 bits of byte 124. So, the next 8 inputs move to the next byte, which is byte 125. Therefore, the 9th input has the address I125.0. The 10th input is I125.1. And this continues until the 16th input, I125.7. So, our 16 inputs are distributed across 2 bytes. Inputs 1 to 8 use byte 124. Inputs 9 to 16 use byte 125. And this is the important rule to remember. When all 8 bits of 1 byte are used, the next digital I/O point continues at the next byte. The same byte-and-bit addressing principle applies to digital outputs. As I mentioned earlier, the PLC output area is identified by the letter Q. When we write an output address, we first write the letter Q, followed by the byte address, a dot, and finally the bit address. Now, let's look at the digital outputs of our CPU 1212C. Our CPU has 6 onboard digital outputs. In our current hardware configuration, the output start address is byte 0. Since 1 byte contains 8 bits, you might expect 8 possible bit positions. However, our CPU has only 6 onboard digital outputs. Therefore, these 6 physical outputs are assigned to the first 6 bits of the output byte, from bit 0 through bit 5. So, the first output is Q0.0, the second is Q0.1, and the 6th and last onboard output is Q0.5. Notice that we are using bits 0 through 5. Bits 6 and 7 are not assigned to onboard digital outputs of this CPU. And just like the input addresses we discussed earlier, the output start address can also be configured in the hardware configuration in TA Portal. We'll see exactly how to check and configure these addresses in the next video. So, for our CPU 1212C, in our current configuration, the 6 onboard digital outputs are addressed from Q0.0 through Q0.5. Now you understand how the wiring works, and you understand how PLC input and output addressing works. In the next video, we'll open TIA Portal and start programming our S7-1200 PLC step by step. We'll begin with the fundamentals and gradually move toward practical industrial applications. As we progress, we'll build real-world automation examples and practical PLC programs that you can apply in industry. So, if you want to learn Siemens PLC programming from the basics and gradually move toward real industrial applications, make sure to follow the next videos. Thanks for watching, and I'll see you in the next video.